Rover's current power units are the envy of the automotive world. The K-series, introduced in 1989, has proved to be highly successful. The latest K development being the exciting variable valve control unit in the MGF. Then there was the fly-by-wire L-series diesel engine at the end of 1994. So smooth and powerful, it transformed people's opinions of diesel engines almost overnight. Now the Rover engineers have done it again. This is the all-new kv6 engine. 2.5 litres of sophistication to power our large car range into the 21st century. And it's what this programme is all about. Let's start by giving you a bit of background to the kv6. It all began in 1991, when it became clear that the existing V6 engine had limitations. One of these being its inability to meet emission regulations proposed for the late 90s. And so the engineers were given a brief to start with the K16 design and produce an all-new 2.5 litre V6. It was codenamed Merlin. Merlin had to be compact, lightweight and reliable, yet outperform the current unit. And of course, it had to meet future emission laws worldwide. The Rover engineers are very enthusiastic about the outcome. The engine has met all their development criteria. The result of their work is the shortest V6 in its class. It's also nearly 30 kilograms lighter than its predecessor. It has more power and torque and gives an average 14% improvement in fuel efficiency. The production build facilities have been carefully thought out too. Instead of relying too much on robotics, as is the practice these days, Rover have opted for a considerable degree of hand building. Obviously, modern machining technology still has a big part to play for production operations such as the cylinder block and cylinder head. But for final assembly, it was decided that this sophisticated engine needed a special build procedure. And a conscious decision was made not to rely on the monotony of the one-man, one-job process. So the kv6 assembly line is manned by a small, hand-picked and dedicated team, skilled in their work and fully trained to carry out all the line operations. Every engine has the same rigorous checks at specified intervals during the build, from a careful matching of piston and connecting rod assemblies to a thorough pressure testing procedure to check for porosity or leakage. After build, each engine is put on a test bed and run for half an hour through a range of tests, and at the same time inspected using special equipment for any signs of oil or coolant leaks under running conditions. Let's look at some of the kv6 features. It's all alloy to keep weight to a minimum, but strength is a vital factor too, and you'll be most impressed when you see inside it. For example, look at this substantial bearing ladder to support the crankshaft. It's made of a special alloy used in the aero industry for strength and durability. It's line-bored with the block, and if ever you have to remove it, you must renew the bolts. There's two types. The outer bolts are shorter and are Torx-headed, while the inners have hexagon heads. The new bolts must be fitted to their correct locations and must be tightened to the right torque in the sequence cast into the bearing ladder. As we said earlier, compactness was one of the design criteria for easy installation in transverse applications. Just look at the short length of the crankshaft. It runs on 4 large diameter main bearings, and the center journals and all the connecting rod bearing journals have cold rolled fillet radii to build in additional strength where it's needed. The main and con rod bearing shells are a selective fit from 5 different color-coded sizes. The cylinder liners are the damp liner design, similar to the 1.6 K-series engine, and are sealed in the block with Hyalomar. And here you can see the cylinder numbers cast into the block. The left-hand bank is numbered 1, 3 and 5 and is on the side nearest the front of the car when the engine is installed transversely. And the right-hand bank is numbered 2, 4 and 6. Incidentally, each piston and connecting rod is supplied as an assembly to service. At the top end, the 2 cylinder heads incorporate the combustion system design, which has proved to be so successful in the K-series. 4 valves per cylinder, hydraulic tappets and separate camshafts for inlet and exhaust. The 2 cylinder heads are identical, although the exhaust camshaft in the left-hand head has this reluctor, which signals the engine position to the ECM. The camshaft drive is very interesting. As you can see here, the drive belt on the crankshaft nose turns the two inlet camshafts and the water pump. And at the other end, these two belts take the drive from the inlet camshafts to the exhaust camshafts. We'll look at timing procedures later in the program. It's not nearly as difficult as you might think. By the way, the camshaft gears are made from sintered metal, and oil is used in the manufacturing process. In service, this oil can be thrown off the gears and create a fine mist on the inside of the timing belt covers, so don't confuse this with an oil leak. Next, the lubrication system. The oil pump is in this housing, driven directly by flats on the nose of the crankshaft like the 4-cylinder K-series. The housing incorporates the pressure relief valve, this oil pressure switch, an oil temperature sensor and the mounting for the filter. This diagram shows the circulation. Oil is drawn up from the sump by the pump which directs it all to the filter. From there, it's forced up to a gallery which runs the length of the block and supplies the crankshaft bearings. The oil is fed through the cylinder heads to lubricate the camshaft bearings via location dowels at the ends of the block. At the front on the left-hand bank and at the rear on the right-hand bank. Now a word about the kv6 engine management. It uses a MEMS 2J ECM, the latest version of the highly successful modular engine management systems used by Rover. It provides full control of the engine's fuel and ignition requirements to ensure that both maximum power and minimum emissions are achieved. Fuel is injected by 6 injectors controlled by a closed-loop sequential system. The injectors are activated individually in the engine's firing order to ensure the right amount of fuel is injected to the right cylinder at the right time. Sequential fuel injection offers benefit over banked and grouped systems by ensuring precise mixture preparation in each cylinder under all speed, load and temperature conditions. Incidentally, to support this sequential injection, the ECM must know the engine's firing position. It gets this information from the camshaft sensor fitted to the left-hand head, which reads from the reluctor on the exhaust camshaft we saw earlier. The ECM also needs an engine load signal supplied by this manifold absolute pressure sensor. It's one of the most critical sensors in the system. Unlike other K-series applications, it's mounted directly on the manifold and connects to the ECM by 2 wires. Next,